Hi, I'm Niall Williams. I'm a PhD student at the University of Maryland, and I'll be talking about redirected walking in static and dynamic scenes using visibility polygons. This is work done as part of my PhD under the supervision of Aniket Bera and Dinesh Minocha. So in VR locomotion, the user is located in a physical and a virtual world at the same time. And usually the layouts of these worlds and the sizes of these worlds are different. And this leads to a fundamental problem in VR where the user will want to travel along some valid path in the virtual world, but this would correspond to some invalid path in the physical world. One way to get around this is with redirected walking. With redirected walking, we can decouple the shape of the user's physical path and their virtual path without interfering with their virtual experience. And so the end result is that by applying redirection, we can steer the user along different paths in the physical world and steer them away from objects without interfering with their virtual paths. In redirected walking, we have a user located in an environment. The user will want to travel along some virtual path, and this corresponds to a range of physical paths that the user can be traveled along. And usually if the user gets too close to a physical object, we initiate what's called a reset, wherein the user just has to turn around after stopping walking so that they can start to walk again once they're reoriented away from whatever object they got too close to. And a redirected walking controller is an algorithm that's responsible for applying redirection to steer the user away from objects and avoid as many resets as possible. This turns out to be quite a difficult problem to solve in practice because the controller is responsible for doing some kind of geometric reasoning about the user's path and the shape of their path relative to objects in the environment, and oftentimes they don't have perfect information. However, it turns out that this whole idea of finding an optimal path relative to some objects in an environment is a very well-studied problem in the field of motion planning. So as the name maybe suggests, motion planning is the subfield of robotics that is concerned with getting a robot or some agent from point A to point B in an environment. And this is a very well-studied problem with decades of research and effort put into it. And this is where our first contribution starts, where we basically show how to use redirected walking in terms of a motion planning problem. So with motion planning, we have an environment and some agent in the environment. For us, this could be either a robot or in our case, a human. And the configuration describes the agent's state in the environment. The state in this work consists of the position as well as the orientation in the environment. And so with motion planning, we have the set of states known as the obstacle space, which is all states that yield a collision with an object in the environment. We also have the free space, which is the set of states that don't yield a collision. So you can think of the free space as the region of the environment that the user can walk around in. And thus, given some goal position in the environment, the motion planning problem is basically just to find some smooth connected path in the free space, so some set of configurations in the free space that takes the agent from the initial position to the goal position. And we can sort of translate this idea of motion planning into the redirected walking setting as well. So in redirected walking, the user is located in both a physical and a virtual world at the same time. And the user will want to travel along some path in the virtual world. And this path corresponds to some path in the physical world, which may or may not intersect with some objects in the physical world. And so if the path intersects with some objects, the motion planning for redirected walking problem is basically just apply redirection to transform this corresponding physical path into some new path such that every configuration along the transformed path is in the free space of the physical environment. So we don't have any collisions with any objects in the physical world. However, if we sort of reframe the redirection problem in terms of motion planning, we have a motion planning problem with additional constraints now. So the first constraint that we have is the maximum redirection constraint. So for any given virtual path, there's a limited set of physical paths that the user can be steered along. And it depends on things like the shape of the path as well as the user's perceptual system. So any path we steer the user on must be within this range. We also have the deviation constraint, the path deviation constraint. So if the user wants to travel along a path that yields a collision in the physical world, there's multiple options for paths we can steer the user along. And usually we want to pick the path that is the least deviation away from the virtual path that the user is traveling along, because this is a more comfortable path for the user usually. And then finally, we have the information constraint. So depending on the VR system setup, we may not have perfect information about the scenarios. So for example, we may not know what the user's physical environment is, or we may not know what the user's future path will be. And all of these things, all these constraints need to be considered for whatever redirection controller we develop. So here's a quick overview of the differences between traditional motion planning and redirected walking motion planning. So in the traditional setting, we have at least one agent, as well as in the redirected walking setting. But in the traditional setting, we have one environment, while in the VR setting, we have two environments. In the traditional setting, there's full control over the agent because it's a robot that we're controlling, whereas in the VR setting, we don't have full control over the agent because the agent is a user, and at the end of the day, they're free to do whatever they want, really. And then usually traditional planning, the constraints are imposed by the mechanics of the robot, so like how the robot works and how it moves, whereas in the VR setting, the constraints are imposed by the user's perceptual system because we always need to respect their perception and keep the experience comfortable for them. And then in the traditional setting, the focus is mainly on efficient and safe paths, while in the VR setting, the focus is on comfortable and safe paths, not necessarily efficient. And so in this work, we have a couple of assumptions when we tackle this redirected walking problem. So first, we assume that we know the layouts of the physical and virtual worlds perfectly. And then we also assume that we know the user's configuration in both of these worlds. And finally, we assume that we do not know what the user's physical or what the user's future path will be in the virtual world. And this is a bit of a problem because the way I framed the redirection problem in terms of motion planning has all been in terms of the user's path through the virtual world and how that relates to their path in the physical world. But if we don't know what their path is going to be, using motion planning can be a little bit hard. So to get around this, we use an idea also commonly used in motion planning, which is the visibility polygon. So if we're given a set of polygons in the plane, as well as some query point, which we show in orange here, the visibility polygon is just the set of all points that are visible to that query point in the plane. And that's this region shown in blue here. And we can think of this query point not as just some random point, but actually as the user's position in the environment. And if we do that, then this visibility polygon is actually a very clean and compact representation of the free space that is available to the user or immediately available to the user. So it's basically a representation of the local area around the user. And using this, we can identify areas of potential collisions before they actually happen without knowing the user's path. So if we consider this pair of environments, for example, the user may want to travel along some path, which could yield a collision with a physical object. And we don't exactly know this, and it may be hard to figure this out if we don't know what the user's future path will be. But we can get around this if before the user starts walking, we compute their physical and virtual visibility polygons shown in blue and red. And then if we imagine sort of superimposing them on top of each other, as we see on the right side here, we get this new image. And what we can see is actually, if we draw the path that the user would have taken, we can see that there's a collision because the user's path crosses the border of the physical visibility polygon. And that indicates that the user would have to incur some kind of collision in order to walk on this path. And so in this case, we're able to, using this technique, we can identify regions that would potentially yield a collision before the user actually walks along that path. And so in this case, if the user just rotates a little bit to their left, now the superimposed free spaces overlap in terms of the region that the user wants to walk in. And now the user is able to travel along that path without any collisions. And this idea is basically the core of our second contribution, which is a new steering algorithm for redirected walking, which is based on visibility polygons. And I'll go over this algorithm now at a high level, and the full details can be found in our paper. So how our algorithm works is that on every frame, we compute the visibility polygon in the physical and virtual worlds, and then we divide up these polygons into regions called slices. And then on every frame, we identify the slice that the user is currently walking towards in the virtual world, which is shown in orange here. And we just consider this to be the slice that the user is currently looking at, because we assume they walk in the direction that they're looking. And then in the physical world, we identified the slice that is most similar to this orange virtual slice, which we again show in orange here on the left. And the way we measure similarity here of the triangles is just through the area of the triangles. And then finally, once we've identified these two slices, we just steer the user such that their heading direction is aligned with the angle bisector of the physical virtual slice that we have found and identified. And the idea here is that we want to steer the user towards regions of space in the physical world that are more similar to the region that they're walking towards in the virtual world. Here's a demo of this in action, and we can see the appropriate highlighted slices in the physical and virtual worlds, respectively. So we evaluated our algorithm in 4 pairs of environments, 3 of which were static and the last of which had virtual objects that were moving around. And we compared against some state-of-the-art algorithms, which are steer to center, artificial potential fields, as well as alignment-based redirection controller. And we considered these controllers because they've shown good results in the past and because they have similar assumptions to our algorithm, so the comparison is more fair. And we found that in all 4 of the pairs of environments we tested, our algorithm yielded significantly fewer resets with objects. And so this suggests that the user would have a better time walking around and avoiding objects with our algorithm than with the other prior algorithms. And so in this work, we did show some nice results, but there are definitely some limitations. So first of all, we only tested a limited set of walking paths, and this is because we had to work with simulation to get a large amount of data. Also, the area metric that we use to measure the similarity of slices between the visibility polygons is quite a crude metric. So better measures of similarity probably will yield better results. We also only tested a limited number of environments, and we only considered the single user case for VR. Multiple users will probably introduce some new challenges that we haven't yet considered. And so in conclusion, we saw with this work that redirected walking is very similar to a motion planning problem. And so there's lots of prior work in motion planning that we can probably take advantage of as a VR community. We also showed that visibility polygons are a great representation of the free space for redirected walking. And finally, we showed that borrowing even basic ideas from motion planning can yield significantly improved results. And we believe there's lots of room for growth because we've barely scratched the surface of motion planning with this work. And we believe that other researchers in this area should take advantage of these ideas from motion planning. Thanks for listening.